Log on, tune in, find out. Another good idea from Cambridge.
And the first talk is Celine Scornavacca.
Okay, hi, so I'm Celine Scornavacca and I'm going to present today a joint work with Franziska Zigman and Daniel Huson of Tübingen University. So this one is like, it's a little bit pleasant problem with respect to the hard, difficult one. So it's always NPR, don't worry, but we are going to draw networks and so as lots of people said already, we use phylogenetic tree to describe the evolution of the species, and we also know that for some kind of evolutionary history, we cannot use this kind of representation. For example, when you have reticulate events such as hybridization, horizontal genes transfer, etc. So in this case, we use phylogenetic networks. So I think if I give again the definition of these two objects, you will kill me. So I will just go further in the presentation. So in systematic biology, we are often faced with the problem of comparing two several different trees, and for example, in co-speciation studies or multi-gene analysis. And there is a way, for example, to compare trees is to compute distance, such as the TBR, SPR distances, triple distance, etc., as we saw yesterday. But there is also sometimes the biologists are interested in actually draw these trees and look at them and spot the similarities and the differences. So sometimes they can be more interested in this kind of drawing than just a value, like a numerical value of similarity. So they use what they are called Tanglegrams, that is just actually a drawing of two rooted phylogenetic trees face each other, and with some lines that we call auxiliary lines that connect matching taxa. And the matching taxa can be, for example, the same species in the two different trees, or in the co-speciation study, there can be different species. For example, here we have a section of ficus, and here the corresponding genera of a pollinating wasp that are connected. So this problem, as I said, is polynomially solvable for the problem where we have that one layout is fixed and only the other can vary, but is NPR and FPT in a number of connectors. In the case two layout can vary, can both vary. So the connector is just another name for auxiliary lines that connects matching taxa. So what we want to do here in this talk is to give a definition of Tanglegram for rooted phylogenetic network, because they are more and more used by biologists. And we want to give this definition in a way that the definition is a generalization of the definition for trees. So I'm going to give you some definition. So what I will call a topological embedding of a network, phylogenetic network S, is a map that assigns to each node of the network an order set of its children. And I'm going to denote by Fn the forest of trees that I can get by deleting all reticulate edges of the network. So I'm going to call reticulate edges the edges that enter in a reticulate node, otherwise I will call them tree edges. So you have to be careful, because these are not forced to be phylogenetic trees, because some label can be, some tree leaves can be a label. So this is why I use the word tree and not phylogenetic tree. And then the topological embedding of this forest obtained by the deletion of these reticulate edges is just a topological embedding of each tree in the forest. So given this kind of tau, so topological embedding of a forest, so here for example we have a phylogenetic network, and here the associated forest Fn. So I call a total order pi on the taxon set not interleaving if these two conditions are both satisfied. So the first condition just said that if two taxa are in the same tree of my forest Fn, then yeah, they have to be in the same order that my topological embedding fixed them. So for example here, this drawing is giving you a topological embedding, and you say that A has to be before D. So if I fixed total order that start with D and then go with A. This is not respecting our tau. And the second condition is just really ugly to see, but what it's saying is that when I have this set of 3, I can have that one set of taxa of the one tree can be inside the other one, but they cannot be overlapping. So here there is an example. Here I have A, D, F, G, H here. Then I start with the second tree, so I, G, J, K. Then I continue with L, then B, C, E. This is good because they are one inside the other. But if I take this one, for example, I have H, then I go I, J, then I go back L, then I go to K. This is not good. These are overlapping. So why I want my total order to be not interleaving is because the fact that I have this interleaving property assure that I can actually draw the network from the embedding of Fn without 3-edge crossing. So why I want to do that is because if you remember, the definition of tangram for trees is without edge crossing, okay? But we also know that some network can be not planar, so I cannot just say I don't want any edge crossing, because otherwise I will have a definition of tangram that can also not exist for some network. So this is why we want that only the 3 edge they are not crossing. Like that, we can use this definition also for tree and it's working. But some crossing that involve reticulate edges are possible. So this is our definition of a tangram for rooted phylogenetic network. So I just wrote it here, the definition, so it's just a system. It's really ugly to see, but what we have to try to find is so a topological embedding tau 1 for Fn1, tau 2 for Fn2, and then 2 non-interleaving total ordering of x1, x2, when x1, x2 are the taxon set, and they both are non-interleaving with respect to their tau. So this is just a little example. So here there is the first topological embedding for the first network. This is the second. For this is the network, in this case it's a tree, and then here I have the order. I just put this example to show you that the topological embedding of this is not giving an ordering complete topological embedding of the network. For example, from V1 we know that V2 is before V3, but then from V3 we don't know how to put V4, so there is another step to do. So, and then we define an optimal tangram, a tangram that so minimize the crossing number here between connectors, and among the one that minimize this crossing number can be also drawn with a minimum cross that involve reticulate edges. So in this case, for example, this is not a tangram because there is a cross between 3 edges. This is a tree, so all 3 are 3 edges. In this case, this is a tangram, but it's not optimal. Indeed, this number of crossing between connectors is 0, okay? But you can see these are the same 2 network and 2 tree, and this is better because the crossing number is 0, but here there is no crossing involving reticulate edges, and here there is 1 crossing. So this is not optimal, but is a tangram, and this is an optimal tangram for these 2 network. So I will have to introduce other concepts before giving you the algorithm that we propose for this problem. So we know that a split is a partition of the taxon set into non-empty set, and so already we saw circular split in the presentation of Philippe, and this is just like we have a set of splits, and we say that are circular. I would just say the informal way, so we can just put the taxa on a cycle, and then we can have the interval on this cycle are the split. So we say that this is the interval realizable also. This is the, and these are really interesting set of splits because this split they can be represented by a split network that is planar. So this is why people like them, and lots of way of producing them. So, and from a set of split, we can get a distance. How? We can just take two taxa from our taxon set and just see the split that separate the taxa and add up, so the weight of this separating split. And then we say that the distance matrix is circular if and only if we can find a circular weighted split such that we can get from this split the our input distance matrix. And so the well-known neighbor net algorithm, given the input distance, give you an ordering of the taxon set plus a set of weighted splits such that this ordering is a circular ordering with respect to the set of splits. And the thing is really important for us, for our algorithm, is that the neighbor net is consistent. It means that if we have a circular distance matrix, then we will get the good weighted split. So the split that give back the distance matrix. So just a little more definition, and I will give you the algorithm. So this is the definition of a cluster set for phylogenetic networks. So this is different from what Stephen talked about this morning, because this is what is called the hardwired cluster representation of a phylogenetic network, while Stephen talked about the software representation. So this is just say that we have like one edge, then we take the target node of the edge, we follow, and all the taxa we can get below this node is our cluster. So it's really easy. So this is the way that I'm going to consider cluster in this algorithm, and then we can get a split associated with this cluster, just taking the cluster versus what is not in the cluster. So this is what I'm going to call in the algorithm SN, so split set of. So finally, we see the algorithm after like 12 minutes. And so we have these two phylogenetic network on two taxon sets. They can be different, and we have a set of connector between this taxon set. So the first thing we do is that we add a dummy leaf to both root of the two network we want to draw. Then we compute a distance matrix that is just the sum of the distance from the splits of the first phylogenetic network restricted to the intersection of the label set, plus the equivalent thing for the second network. Well, what we do is finally, this is where a neighbor net appears. We obtain a circular ordering from this this matrix H using neighbor net, and then what we do is we break this linear ordering using row. So we have loading. We don't know how to break it, and this is why we add this guy over there. Exactly why. And then we have an ordering that I don't remember exactly how it's called that in Greek. Psi. Thank you. Okay. How are you using this weird letter? Okay. So from now on, I'm going to give you so the procedure for for N1, but the N2 is exactly the same thing. It's just that otherwise I would have two different screens. So first of all, we get the forest Fn1 by deleting the reticulate edges from N1. So here there is an example. We get this guy that we have. So we called this, if you remember, so pi was the linear ordering once we break it. So we would like to have this linear ordering. So what we do is that for each of these trees of the forest, we determine a topological embedding that minimizes this number. The idea is that we want to be as much as possible in agreeing with this pi. So sometimes it's not possible to have it exactly this ordering because it's given by a neighbor net. So this ordering can be impossible to realize. But we want to try to order these guys inside, trying to be as much in accord with the pi. So we do that for all of these trees, and we get so our topological embedding tau 1 for all trees in F and 1. So what do we need to now do is to obtain the total ordering of x1, and then we do that by finding a non-interleaving ordering with respect to tau 1 that minimize again this value that is just that is as much as accurate as possible with pi. So there are lots of other things that I cannot enter into detail and I cannot explain you. For example, how to do when these two sets are different. There are some little escamotage that we have to use, but I don't think I have the time. So why we use neighbor net? So this is something that the reviewer asked. I think it was really obvious for the way that we wrote in the paper, but this is exactly why we do that. Is that if we have a planar Tanglegram, it means if I can put the two rooted phylogenetic networks and they are both planar, and also the connected auxiliary lines are not crossing, then in this case the fact that I use neighbornet to get an ordering assure me to find a solution without any crossing between edge connectors. So if there is a solution that is planar, then I get the good solution. So like my reviewer again, it said this is just a particular case, but you have to think that this is also in the case of trees is the only case that we are sure to have the optimal solution. So the only thing I found in the literature that you can find for sure the optimal solution is where there is a zero solution, we can find a zero solution, but that's it. And actually I told you how to get this ordering, this embedding, but how to actually draw a tanglegram. This is another fascinating problem, but I don't have time and I don't want to upset her because she's really, really ugly. I also think it's a man indeed, but I don't know. So, but it's really, really interesting how also to draw them. I think the next people in the next person also will talk about drawing phylogenetic network. Is not really easy because biologists want them to be nice. So you cannot just put stuff with all reticulated edges, stuff crossing. People are not going to use that in their paper. So I just want to show really, really fast that we made some simulation. So here there is the time, and here is like how good is the method. So I think it's really too little to see. But the thing is that we use for this we use binary trees because the best method available for tanglegram for trees are restricted to use binary trees. So our algorithm is really good, is really fast also for tree. So also if it's designed for general network that can be also not binary, is still working pretty well. And then we also did some simulation. So here we have like three variants of our algorithm that I don't have time to explain, but we are still pretty good in the case. But in the case of network, the problem is sometimes we have like some instances that are where the crossing is really, really high. So, but you have to think that, for example, if you have two phylogenetic networks that have like 200 taxa, and then you just misplace one taxa, then you will have to cross all the others. So these numbers you can think that they are really high for some distance, but they're still pretty good when you watch at them. And yeah, this is just an example. So here they use this, they just draw it. These poor guys, they were there and drawing the tanglegram by hands, and they still also, I think they worked a lot, but they get a really crossing number really high. And when they try to understand if there was an hybridization in this genera, then it was really difficult to check when you read the paper. And then we just like to put the network inside. It's pretty nice like that, I think. And the crossing number is really low. So I think it is a nice tool for biologists, and thank you for your attention.
One very short question. Dan.
Yes, that was very nice, very impressive. I missed the very beginning, so I don't know whether you mentioned this, but there is a paper that that does non-binary and does optimality that's beyond the planarity, and that's a paper by Catherine St. John and others. Did you look at that?
Yeah, it's just, but they don't use they don't do a
Not
network.
networks, no, but trees that are not
Yeah.
binary.
I just said that the best tools are for binary. When I actually like use them, and I just show that. But I know there are some work that are not for just binary. A few, but they are.
Okay, so thank you very much.